right, good morning, everybody. Welcome to the National Air and Space Museum during World Space Week. We'd like to start off this morning's event by introducing Dennis Stone, who's the chairman of the World Space Week. He works at the Johnson Space Center and coordinates activities across the country in honor of World Space Week. So, Dennis? Good morning.
Thank you, Jim. Yeah, we have our slides, please. I want to give you a very short introduction. Happy World Space Week to everyone. World Space Week is October 4th through 10th of each year. It was declared by the United Nations General Assembly, next slide, please, in 1999 in the Vienna Declaration. All the nations of Unispace 3 got together and agreed on this as a global celebration of the potential of space. Next slide, please. And so since the first World Space Week in 2000, it's grown to become the largest space event on Earth. Last year, we were in 80 countries with 1,400 events of all kinds. And over the last 6 or 7 years, we've had 2 million attendees and nearly 1/3 of a billion media impressions. Next slide, please. So let me show you some results from last year, because we're right in the middle of World Space Week, so I don't have a lot of pictures to show you from now. I'm sorry, the goals, of course, of this synchronization is to educate the public about the benefits of space, inspire the workforce of tomorrow using space, demonstrate public support for space, and promote organizations that are involved in the space program. Now, next slide, let's talk about the results from last year. The theme was Exploring Mars, Discovering Earth. Next slide. And so this was celebrated all around the world. So here in India, they were launching rockets. They didn't make it all the way to Mars, unfortunately, but it was still a great stimulating event for the kids. Next slide. Here in Austria, there was a mission control center, if you will, for simulated Mars missions that were being held all over the world. Kids would go out, wear little make-believe spacesuits, and pick up make-believe Mars rocks and learn the scientific method of geology. And that was a great event. Next slide. Pakistan, there were some events particularly to stimulate female interest in science, technology, engineering, and math, STEM as we call it, as well as a big conference by Pakistan's space agency. Next. Also in China, a very large event here with Buzz Aldrin, 500 students, media packed the room to celebrate space in China, and that is a big deal for them. Next slide. And even in developing countries like Libya, they don't even have a space program, and yet they still celebrate the great potential that space has for them and their children's future. So this is going on all around the world this week. Next slide, World Space Week 2014. The theme is Space Guiding Your Way. And so how appropriate that NASA and the National Air and Space Museum today are featuring space navigation. And so that fits perfectly into our theme. But clearly, space navigation has changed the world, and so the world is celebrating that great change this week during World Space Week. So if you want to see what's going on, use Twitter, use Facebook, go to our website. There are events all over the world. We encourage you to join the celebration through October 10th. Happy World Space Week. Thank you very much.
All right, thank you, Dennis. Now I have the privilege of introducing our first speaker today. Dr. Joseph Lazio is the Chief Scientist of the Interplanetary Network Directorate at the Jet Propulsion Laboratory managed by the California Institute of Technology. He received his PhD from Cornell University and worked at the Naval Research Laboratory as a National Research Council Research Associate and radio astronomer before joining JPL. He served as the project scientist for the Virtual Astronomical Observatory. He was also project scientist for the Square Kilometer Array and deputy director of the Lunar University Network for Astrophysical Research, part of the NASA Lunar Science Institute. He's currently the deputy principal investigator for the proposed Dark Ages Radio Explorer, or DARE mission, which, if approved, would be a lunar orbiter designed to search for the effects of the first stars on the gas from which they formed. He also observes routinely from the world's greatest ground-based radio telescopes, including the expanded Very Large Array, the Very Long Baseline Array, the Green Bank Telescope, the Giant Meter Wave Radio Telescope, and the Australia Telescope Compact Array. So let me welcome Joe Lazio.
It's a great pleasure to be here at the National Air and Space Museum. I always get a real thrill coming to this building, and it's particularly appropriate that World Space Week is happening here. The first slide is the title slide, and the idea here is to describe to you how the Deep Space Network has been an integral part of NASA and humanity's exploration of the solar system for 50 years. Thus, on the next slide, in fact, I just stated the thesis. The idea of what I'm going to try to convince you of is that the Deep Space Network, the DSN, has been, is, and will continue to be an integral part of our exploration. What is the Deep Space Network? The next slide shows that the Deep Space Network consists of complexes at Madrid, or just outside Madrid, Spain, just outside Goldstone, California, and just outside Canberra, Australia. These are set up at each complex. There are multiple, as the pictures at the bottom of the screen show, there are multiple very sensitive antennas. These are required to communicate with very distant spacecraft. And there are 3 complexes so that any spacecraft anywhere in the solar system will be able to communicate with the Earth, or we will be able to command it to do whatever we want to do. Next slide. This is, in fact, our 50th year. The Deep Space Network was formally established by then Director of the Jet Propulsion Laboratory, William Pickering, on 1963, December 24. So we are considering this to be our 50th celebration year, as it were. Of course, the question you're probably all wondering is, what was he doing on Christmas Eve? The joke, at least I think it's a joke, is that there is a rule within NASA that all important mission events must happen on or near major holidays, so that Dr. Pickering had no choice in the matter. The foresight, however, that is shown by setting up the Deep Space Network in 1963, let's just take a look on the next slide at some of the communications infrastructure at the time. The Soviet Union and the United States had a hotline between Moscow and Washington. That's the thing shown on the left of the slide. But it's not actually a red telephone, it's a teletype. And suppose my grandparents had tried to call the family back in Italy. Well, you could talk internationally, but at times the communications was a bit iffy. Just as well set the context, what else was happening in 1963? The next slide shows that, in fact, we began to appreciate French cooking. The next slide, I can't say 1963 without acknowledging there were some sobering events that happened that year. And on the next slide, 1963 is also a pivotal year for NASA. This is Gordon Cooper. He rode the last Mercury mission, Faith 7. And this is the end of the Mercury program. NASA is now in the process of transitioning from Mercury, which was just to get humans into space, to the Gemini program. What needs to be proofed, prototyped, demonstrated to actually send humans to the moon? The next slide now starts that journey, and the Deep Space Network was an integral component of it. Before you send humans someplace, you need to send a robotic spacecraft there. Ranger 7 was the first mission that we actually made it to the moon. So here are pictures as Ranger 7 was going into the moon. It's made what is euphemistically called a hard landing, but you might also call that an impact. Nonetheless, those pictures came back through the Deep Space Network, so we could actually get our first close-up glimpse of where astronauts would eventually be standing. On top of that, Ranger 7 made it to the moon. That's an important aspect. In order to do any kind of deep space mission, you have to navigate. You have to go from the Earth to the moon or to Mars or wherever it is you want to go. And the way we do that is by using the communication signals, the same signals that are used either to command the spacecraft or from which we get data. We also use to tell us where is that spacecraft, and then as well make changes or tell it to make changes if it's not quite going where it's supposed to be. So an important aspect of the DSN is not only the communications, but it's also the navigation. The next slide is then, of course, over the 60s, there were multiple robotic missions to the moon, and eventually, of course, humans landed there. Neil Armstrong becomes the first human to step out. The Apollo mission was, of course, not only a triumph of technology, it was also a scientific bonanza. They brought back rock samples that completely revolutionized our understanding of the Earth-Moon system origin. They put the first telescope on the moon. And importantly, the DSN was a partner in that. Now actually what NASA originally did was set up something called the Manned Spaceflight Network, which was supposed to be somewhat of a partner. But as time carried on through the 60s, the Manned Spaceflight Network started sharing space and eventually ended up effectively merging into the DSN. Next slide. Okay, that was then. What about today? What is the DSN doing today? Next slide shows that the DSN is a partner on something like 36 missions spread across the solar system. So you see on the bottom row we have missions either en route to or at various planets. I'm not sure if you can see it, but the middle panel on the middle panel on the left, that is actually ESA's Rosetta spacecraft, which is currently orbiting a comet. So this is an important aspect. The DSN, although it's a NASA communications infrastructure, in some sense, it really is part of humanity's infrastructure for exploring the solar system because we partner with the European Space Agency on some of their missions. The middle picture of Mars has actually been brought back by the Indian Mars Orbiter mission. And again, the DSN has been a crucial link in the communications to that mission as well as navigation to it. In the upper right, that's the Voyager spacecraft. We continue to communicate, in fact, that's Voyager 1. We continue to communicate with Voyager 1, which is now arguably outside the solar system. I mean, think about that. We have a spacecraft that is outside the solar system. We are actually starting to probe into interstellar space, and I can say that. There can actually be journal papers written about this because of the data that have been streamed back through the DSN. Then finally, Chandra in the upper left, that's a mission, that's actually an X-ray observatory, so we use it figuratively to explore beyond the solar system, look at things like the environments of supermassive black holes or exploding stars. This is commanded, and then the data, the scientific data from it are received back through the DSN, and then following me, Eric Smith is going to talk about the James Webb Space Telescope, the next NASA great observatory. It as well, in order to get away from the Earth, is going to go out into deep space. The next slide, or the slide that's up currently, actually, the slide that's up currently is part of the first communications test that the DSN did. It did very powerful transmissions just to test communications, and it was very quickly realized that as you start beaming radio waves out, you can essentially use that as radar. And the DSN has now effectively bounced radar waves off almost every solid body of substantial size in the solar system. What you see here is the asteroid 1998 QE2, and you can see the value of doing this immediately. By bouncing the radar waves off, as soon as we get those data back and process them, well, we get the approximate size of the object, we get its rough shape. You can tell in this case, see that little moving dot? That's a moon. A moon was discovered, and I'll gloss over the technical details, but we could in fact determine the mass. The other thing that is perhaps not immediately apparent from this slide, by lighting up that asteroid, we get the distance very precisely and we know how fast it's moving. Thus, we know its orbit. I can tell you with very good confidence that this asteroid is not going to collide with the Earth today or next year or next decade or even next century. And that's important because last year, there was an asteroid that hit the Earth last year, or actually exploded in the atmosphere over Russia. And that highlights the importance of determining of the orbits of asteroids, is because that's a crucial aspect of protecting life on this planet. And indeed, it's a bit sobering. This asteroid exploded in the skies over Russia in 2013. What would the world be like if that had happened in 1963? Next slide. The other aspect of the Deep Space Network is, and this was recognized very early on, suppose you have a spacecraft, as it's going behind the planet, going behind a planet, say, you can no longer communicate with it because there's a planet in the way. Suppose the planet has an atmosphere. Well, as the signals pass through the atmosphere, they're potentially corrupted. Now, if you're trying to command the spacecraft to get back scientific data, you might immediately think, oh, this is going to be a potential problem, right? Now my signals are corrupted. Or you can take the other approach and say, wait, if I can understand how the atmosphere is corrupting those signals or affecting those signals, then I can understand the planet's atmosphere without actually sending a probe into it. So if you just go forward one, it's effectively, it's making lemonade out of lemons. You've got a corrupted signal, but you can actually turn it into science data. You can study not only planetary atmospheres, but remember, a spacecraft's path or its trajectory is determined by the gravity of the body that it's near, which is determined by the mass inside it. So by tracking very precisely those communication signals, we can in fact study the interior of objects. And the next slide shows one of the great examples of this, turning a spacecraft and the DSN into a major science instrument, or a solar system-sized spacecraft instrument. So next slide. That's what I've already said. Next. Yeah, so this is one of Saturn's moons, Enceladus. And the Cassini spacecraft is currently orbiting Saturn and every so often passing by various moons. It was clear very early, well, actually in a recent pass by Enceladus, at the South Pole, you see these jets of material, and it became clear that those jets are water. Well, that's kind of interesting, right? There's water coming off this moon. And by now, presumably, your eyes have all been attracted to that little blue spot, or that little blue section at the South Pole of the moon. Again, by tracking the signals from Cassini very precisely, they tracked how the gravity of this moon was affecting its path, and it's quite clear there needs to be a subsurface ocean under Enceladus to provide this water. Okay, that's, first off, it's just really cool, right? And then on top of that, think about what that implies in terms of potential habitats in the solar system. Where there's water, is there life? Certainly true on the Earth. And this is Enceladus, Saturn's moon. But in fact, two other moons of Jupiter, Europa and Ganymede, are now known to have subsurface oceans as a result of a very similar technique. So the entire question of is there life in the solar system as a result of some of these kind of science investigations has taken on a whole new avenue, or a whole new window, as it were. Next. I think in the interest of time, I'll gloss briefly over this, but the other aspect is there's a prediction of Einstein's theory of general relativity that is still untested. And by monitoring very precisely the separation between a DSN antenna and a spacecraft, you can check to see whether they're oscillating back and forth, which would be an example of gravitational waves, which is again an as yet untested, or I should say unconfirmed aspect of Einstein's theory of general relativity. And the DSN has been an integral part of taking part in some of those experiments. Next slide. And finally, NASA is some of the next human missions for NASA. They're thinking about going to asteroids. Again, what did I say? If you're going to have a human, you want to have a robotic mission first. We've already sent one spacecraft called near Shoemaker to the asteroid 433 Eros. We've probed a lot of the surface of it. You can actually see here the surface pictures that were communicated back through the DSN. The same technique of probing its interior was used here. And on top of that, the spacecraft was actually commanded. It was not originally intended to do so, but it was commanded to land on the surface of the asteroid. And I think that speaks to the testament of the people who build the spacecraft as well as the DSN, that these systems are agile enough that we can do things that were not originally intended. Next slide. Okay, where are we going? What did Yogi Berra say? That prediction is tough, particularly when it's about the future. Your crystal ball is perhaps no better, or mine is perhaps no better than yours, but on the next slide I'll show you one of the things we're working on is laser communication. There's been a steady push to go to shorter and shorter wavelengths, shorter radio wavelengths, and then ultimately moving to optical, or actually technically infrared. But the idea is by going to shorter and shorter wavelengths, you can pack more and more information into it, and there's always a desire to get back more science information. This idea has been tested already in cislunar space, that is on a spacecraft that was headed to the moon, in an experiment up to this International Space Station. It's not yet been done in deep space, which is what we need for missions to other planets, say. But NASA's probable next mission to a planet in about 2020, or launching somewhere in the 2020 timeframe, is likely, or potentially likely, to carry such a payload that can be used for technical demonstrations. Next slide. The other thing that I find very exciting is constellations of small sats, or CubeSats. CubeSats, officially a 1U CubeSat, is something that's about this big. It's about 10 centimeters by 10 centimeters by 10 centimeters. And in fact, they're stackable, so you can get something like a 3U that's 10 by 10 by 30. But the idea here is we've done the onesies and the twosies, right? We've sent a spacecraft to this planet. We've sent a spacecraft to that planet. I think we need to be moving to the time when we have fleets of spacecraft around planets. We have that at Earth. We should be moving to the time in which we actually have fleets of spacecraft around other planets probing their atmospheres, or probing aspects of them. And these CubeSats, in fact, the top picture shows 3 CubeSats that were kicked off the International Space Station recently. They offer that possibility, so you could have a mission going to a planet and actually carrying, say, half a dozen or a dozen little spacecraft with it. The challenge from the Deep Space Network aspect is that and historically, we've become accustomed. You talk to this spacecraft here, and then you talk to this one here, and you talk to this one here. What does it mean operationally when you're talking to a dozen over here, and then 2 dozen over here? So that's actually, I think it's an interesting challenge. It's a good challenge to have. We're working on it right now. In fact, in some level, there are 5 spacecraft right now orbiting Mars. So we're starting to build up. How do you do that? I think I've said what I need on that one, so next slide. And then finally, beyond the moon. I mean, humans, we went to the moon for the past past couple decades. We've been on the International Space Station in essentially low Earth orbit, but now there's an interest in moving beyond low Earth orbit into cislunar space and into deep space. So next slide. There are multiple possibilities there. The first one appears to be a mission to an asteroid, but long-term goals, of course, Mars. And the idea is that when we go into deep space, we will need the communications, we will need the navigation. I'm confident that the DSN will be an integral partner in all of that. So I think my final slide is the one that I said I was going to hope to convince you, but I think let's cut to the website. If we can cut to the website, there's an actual website that shows the spacecraft with which the Deep Space Network is communicating right this minute. So there you have the three complexes, and you can see the space, all those little wiggly lines are the ones where we're actually communicating with spacecraft right this moment. This is a public website, so you can get to it from your home. Goldstone is not currently operational because I believe it's a maintenance day, as well as there are some NASA personnel out there taking a tour of it. So I'll close with that, and then I believe turn it back over to our MC, Jim Shear.
All right, thank you. Thanks, Joe. One other point to note, Joe was talking about the Apollo 11 mission, first landing. It's interesting to note that there is still one instrument that the Apollo 11 astronauts placed on the moon that we are still using today. They placed a laser retroreflector, a mirror on the moon, that we are still using lasers to bounce off of that and measure the distance to the moon today. So helps you debunk the Apollo hoax theory. Now let me introduce the next speaker. Dr. Eric P. Smith is the James Webb Space Telescope Deputy Program Director at NASA headquarters. Prior to becoming the Deputy Program Director in 2010, he was both the Webb and Hubble Program Scientist. In that role, he was the senior NASA scientist responsible for the Webb science content and was also responsible for monitoring and managing the science program for both the Webb telescope and the Hubble Space Telescope, ensuring that their missions remain viable and true to NASA's strategic objectives. As program scientist for the Webb, Smith was responsible for the definition and safeguarding of the Level 1 science requirements for Webb. He'll tell you more about that. These delineate the essential capabilities that the observatory must possess, such as the primary mirror size, instrument complement, and mission lifetime. Before coming to NASA headquarters, he worked at the Goddard Space Flight Center on the science team for the Space Shuttle-borne ultraviolet imaging telescope and on the data archiving and distribution system for the Hubble Space Telescope. He was also the Webb Deputy Project Scientist from 1996 to 2001. He holds a bachelor's in physics and astronomy from the University of Virginia and master's and PhD degrees in astronomy from the University of Maryland College Park. So let me welcome Dr. Eric Smith to the stage. Eric.
Thank you. Yep. Okay, so how many folks here have heard of the Hubble Space Telescope? Just, quick show of hands. Yeah, I figure most people have. And so just to alert you to something that's going to be happening over the next year, April 24th next year will be Hubble's 25th anniversary since its launch. And so there's going to be a lot of events occurring over the next year to celebrate that. But as fantastic as Hubble was and still is today, there are some things that Hubble cannot see. It runs out of aperture in some sense. There are some things that are too faint for it to see. Its mirror can't collect enough light. And there are some things that it needs to be able to see in different wavelengths of light. In particular, when Hubble took an observation that many of you have probably seen, it was the deep image, humanity's deepest peering into the universe. That Hubble deep field told astronomers, told scientists that we hadn't yet seen the first stars and galaxies that formed in the universe. So at that moment, and that was in the sort of the middle of the 90s, we knew that we had to build a different kind of observatory if we wanted to see those first stars and galaxies. And that's the telescope we're working on today, and that is the James Webb Space Telescope. Like Hubble, it's a partnership between NASA, the European Space Agency, and the Canadian Space Agency. Canada and the many countries you see represented there by ESA will contribute science instruments, and we have those right now. They're 10 miles from us right here now at the Goddard Space Flight Center where they're undergoing testing. And they'll provide scientists to work at the Space Telescope Science Institute to analyze the data. And Europe will also be providing our ride into space. We'll use their Ariane 5 rocket to launch from Kourou to get to our orbit. So if I could have the next slide, please. You heard a reference in the introduction about the level 1 requirements for Webb. Well, that's just sort of NASA speak, government speak for what are the things that scientists want to do with this? What do they imagine this telescope is going to be capable of? And we'll use those scientific goals to guide the engineering and the development of it. And so you see along the bottom of the slides up here to your left or right, 4 questions or 4 themes that we want to explore with the James Webb Space Telescope. The first one there on the far left is called First Light. This is the sort of the primary objective that we have for Webb, the reason why we have such a large aperture. The next question is, because we can see those first galaxies, we can now trace the cosmic evolution of galaxies as they are first born and as they evolve up to today. So this is the first time you have a single facility that can trace that entire history. And so that's what we call the assembly of galaxies. Because we're looking very far out into the universe to see the first galaxies, our telescope has to see in the infrared, because the expansion of the universe has stretched the light coming from those first objects into the infrared part of the spectrum. The other benefit you get from observing things in the infrared is that you can see through some dust clouds in our own galaxy. And so we'll have a facility that's very well tuned for peering into the dust clouds that enshroud forming stars, stellar systems in our own galaxy. And so that's the theme there, the birth of stars and planets. We can use Webb to do that. Again, large aperture to collect the light in infrared. And then the last theme was when Webb was actually being conceived, it was thought we would use it to look at objects in our own solar system, and indeed we will. But since the time of the initiation of the Webb project, which was 1996, exoplanets have been discovered in multitudes. There are thousands of them, and NASA has other assets that are going to be looking for systems with nearby ones. And so we will use Webb to study these exoplanets in a fashion similar to what Joe talked about when he said he was able to use a spacecraft as it went behind bodies and peer at what's happening to its emitted radiation. What we're going to do with Webb is watch an exoplanet, and if I'm the exoplanet and this is my host star here, right now, if you were to observe this system, you would see the light, the spectrum of light from the host star coming into, in this case, the James Webb Space Telescope. But as I come around, at some point, I'm going to start blocking the light from this star. And as it goes through the edge of my jacket here, you might be able to tell what my jacket is made of by seeing what light my jacket subtracts from the spectrum of the star. So even though we didn't plan to have Webb be an exoplanet machine, it turns out the instrumentation we have on it will be very well suited for that. So ironically, the 2 biggest contributions we expect from Webb are at almost the extreme edges of the universe, the very first stars and galaxies that form, and the atmospheres of nearby exoplanets. I like to say that we may be the first telescope that can take a deep breath of an exoplanet atmosphere, because we'll be able to see what the chemical constituents are for some of those if we are fortunate enough to have a nearby one to do so. So if I could have the next slide, please. This is just a diagram of what Webb looks like, and it probably doesn't look like many telescopes you've seen before. It looks a little menacing, in fact. We don't have a tube. Most telescopes, if you think of optical telescopes, have a tube, and that tube serves to protect the mirror from scattered light. You're looking at something in the cosmos, you don't care about scattered light or things around it. So you have a tube to block it out. We don't have a tube here. We're an infrared telescope, so we want to be far away from infrared sources of light, heat. So we're going to go to a place called the L2, the second Lagrange point. It's about 1 million miles from Earth. If you imagine drawing a line between the Earth, the Sun, the Earth, and 1 million miles out, that's the Sun-Earth L2 point. That's where we're going. It's about 4 times farther than the Moon. But what that means is we can now arrange it so that the Moon and the Earth, 2 sources of infrared radiation, are on one side of us, as would be the Sun. So we don't need a tube, we just need a sunshade. And that's what that big diamond-shaped structure is. It's 5 layers of mylar. It's about the thickness of a plastic bag. It's about the size of a tennis court. And that protects us from infrared radiation. So we don't need to have that tube that surrounds the mirror, which is the gold hexagonal structure. Because Webb is so big, it's big because it needed to collect this faint light from the early universe, it's too big to fit in a rocket as a monolithic telescope. So we've made it out of hexagonal segments that are about 1.3 meters on a side. There are some of those at the Goddard Space Flight Center, in fact. And we fold the telescope up to fit inside a rocket. That sun shield itself is all folded up when we launch, and that is another unique aspect of Webb. This way we are folded up, sort of an origami telescope, if you will. And if I could have the next slide, we'll see what it looks like as it heads out to its L2 orbit. So these are all the things that have to happen over the course of a couple of weeks. You'll see a timeline along the top of when things happen. So Ariane vehicle has left us go. We've separated from our upper stage. And so we're about half an hour in, and our solar array comes out, so we have power to do the rest of our activities. These are all the little attitude changes. Along the bottom, you can see where we are relative to the Moon. Of course, the next thing we want to do so we can talk to the DSN that Joe described to you is we have to put our antenna out. And so the next sequence, there's a release of the antenna from the side of the spacecraft first, because everything is held in for the launch so that it doesn't vibrate around. And then at some point, you'll see along the bottom of the spacecraft, a little antenna will deploy. That antenna is about yay big. Here we come. So there's the antenna, 1 day into our deployment. That's so we can have a high bandwidth communication. We have other antennas on there that can talk at a low data rate, and I'll talk a little bit more about that. So now we're past the Moon. Day 2, we're now farther than any human has ever gone there. And now you can see the sun shield starting to deploy. So it's, of course, very sped up here, but this is a very slow and deliberate process because you want to make sure you know where all pieces of that tennis court-sized plastic baggie is at any given moment. And all this time, although you can't really see it in relation to the thing along the bottom, we're keeping the sun behind us because you don't want sunlight to get onto the mirrors of the telescope, because if any sunlight were to get into the sensitive cameras and spectrographs, they would destroy the detectors in them. So now the telescope lifts away from the spacecraft here, and the spacecraft has some residual heat, so you want to separate yourself from that as much as possible. Little covers on the sun shield fold back. They have Teflon springs that release, and they furl up on either side. And then we begin to pull the sunshades out from the spacecraft. We do it one side at a time. And I like to say, of course, this is exactly what it would sound like in space, total silence. Once the sunshades are out, then you need to separate them. There's 5 layers, and there has to be space in between them so that the sunlight that hits the bottom layer and gives it some heat has a chance to radiate out into space. And so the layers are separated. They're about this far separated in between each one, and they're slightly V-shaped, so the separation at the edge is greater than the separation in the center. We have a little, what's called a momentum management flap in the back. That is actually a way that we sail on the solar radiation. That's to balance the radiation pressure from sunlight, which could actually tip the telescope over. So you have to have something to sort of counterbalance that, in addition to the systems you have within the spacecraft to maneuver it, reaction wheels and propellant. One instrument needs a little cryocooler, a little refrigerator, so that starts up there. Now you see the secondary mirror deploys down. This is out at day 6, so we're 6 days after launch. And there's a little radiator panel flips out in the back. That's to help cool the detectors in the instruments. And then finally, the last 2 things, the drop leaf table sides fold up, as it were, to give you the complete mirror. So these are all the major deployments. There's lots of little maneuvering of those mirrors that's going to occur at this point so that they come precisely into focus. But those aren't very exciting to see. And now, in about 30 days, so in about a month, we get out to our L2 point. But most of the excitement's over in the first week. So we don't have 7 minutes of terror. We have like a week long of slow terror, I guess, in that case. How does the DSN work into all this? Well, once we launch, we're going to be using 2 radio frequencies to communicate, so-called S-band and Ka-band. For different data rates. And so we'll be using the DSN to communicate both our scientific data, but engineering data as well. And early on, we'll also be collaborating with Europeans to use one of their stations in Africa. And so you can see there the DSN, the Deep Space Network antenna, is right in the center of that picture on the bottom, and it talks about how they're going to communicate with the spacecraft. But that is the main way that we're going to know what Webb is looking at, is to use the DSN, which is actually different than Hubble, because Hubble's in low Earth orbit. It doesn't need to use the Deep Space Network. It uses tracking and data relay satellites, again, just because it's much closer. It doesn't need the capabilities of the DSN. Next slide, please. So this is what our antenna looks like, a very thrilling CAD diagram of it here, but I just wanted to show you this to show you the complexity of the deployment mechanism. Again, many spacecraft will have just a body-mounted antenna, and so it's a relatively simple thing. Because we're stuffed into this rocket, even our antenna has to deploy down. Next slide, please. And so now these are just some of the pictures of the actual state of the hardware. So these 2 gold cylinders you see are the deploying and rotating motors that go on that. So those are built, and they're now waiting for their next step of assembly. And the next slide, please. These here, again, you can sort of ignore the words on there. What I wanted folks to look at were the pictures along the bottom. Those are, in the case on the left, a spare or a demonstrator model of the main antenna, and then on the right is actually the flight antenna. Since this is a fairly old slide, the flight unit now actually looks like the demonstrator unit there. It's all built up. In the next slide, I mentioned there are other ways that we can talk before we get our main antenna deployed. This is a little tiny antenna. It's about the size of your hand. There are several of those all over the spacecraft. They don't need to be pointed, but that's how we'll talk to the Earth before we actually deploy the main antenna. And the next slide, I think, is just, so this is the schedule for, where are we in the development. You can think of 3 big components as we put it together: the telescope, the science instruments, and then the spacecraft, which holds the sun shield. So in 2014, we have the science instruments all together. They're being tested out at the Goddard Space Flight Center. The telescope, we're practicing building a telescope on a practice unit, but next year we'll start assembling that telescope at Goddard. And the spacecraft itself is being put together out at Northrop Grumman and Redondo Beach in Southern California, along with the Sun Shield. And there you can see we have a 2018 launch date out of Kourou. Next, please. This last one just talks in a little more detail if anyone wants to geek out on the actual communication parameters. Here in World Space Week, we both look back and look forward. And I think Joe gave you a nice overview of how important the Deep Space Network has been to all the activities we've done over the past 50 years using it. And Webb is one of the first instances of how we're going to be using it for the next 50 years. And it promises to revolutionize astronomy in the same way that Hubble did. And if we're lucky, we'll have both of them working at the same time using two different ways to talk to us here back on Earth. So thank you very much.
All right, thank you, Eric. At this point, I'd like to ask both of our speakers to come back up on stage, and we'll have a question and answer period here. And that includes questions submitted from anybody listening to our webcast. So we've got one question asked by one person listening to the webcast, which Eric just answered, which was, what is the James Webb's launch date?
Okay. Yes, so currently our launch date is forecast for October 31st, 2018. And that's out of Kourou in South America. And we have what's called a contingency to that launch date, meaning we have some spare time of about 11 months. So that if everything performed perfectly, we could actually launch early. But one thing we've learned in the space business is nothing ever goes perfectly. So we have margin to that launch date, and we feel pretty good about that.
And as a follow-up to that, how long do you expect it to take to get into position in the L2 orbit and checked out before it goes into science operation?
It takes about 1 month to get out to L2. Then we have what's called a commissioning phase for 6 months. So from launch to 6 months, that's when we're trying out the instruments, we're making sure everything's performing as expected. We'll start taking data about after a month, and you'll often see those are referred to as early release observations. And so that's where the astronomical community gets together and decides what's going to be a beautiful picture to release. So sometime within the first 6 months, you'll see data. But after 6 months is when we'll turn it over to the science community. And then just like for many other telescopes, people will write in proposals, what they want to observe and why they want to do it. And there'll be a competition, and that's how we'll see it.
Scheduling time on the telescope for all of the scientists who want to do observations.
Yep.
So we can look forward to perhaps the first scientific results coming out of James Webb by late 2019.
2019, yeah.
Okay, thank you.
My question is, and you mentioned the 7 minutes of terror, which we all enjoyed immensely because it turned out just fine. Do you have a plan B?
For us, because we can't go to the James Webb Space Telescope, at 1 million miles away, no country on Earth has a way to get there. So that means that every deployment we have has redundant motors on it. So there's not just one motor that pushes the secondary down, but there's a spare motor that if the first one doesn't work, we can do the second one. Many of these motors we can also back up to. Now there are some that don't do that. So in that case, we have a very rigorous program here on Earth before launch of essentially building practice parts of the observatory. So that's why we're building a practice telescope, and we'll practice with the deployments on that to learn how these motors behave, what are the kinds of things that might make them stick, and how would we get around it. So it's a combination of doing a lot of practice building here and then building redundancy into those things that have to move once we get in space. And I can just also add on, Northrop Grumman, the company, has built many things that deploy. Most of them are defense related, and I don't have any clearances, so I'm not telling anything out of school here, but they have said that this is not the most deployments they have ever done on an observatory.
If I could ask a follow-up question to that. The human spaceflight exploration is working on developing the Space Launch System and the Orion crew vehicle with a first launch in 2018 right now. And so they would actually become operational in the same time frame that James Webb will be operational. Has there been any consideration given to making that James Webb servicing a mission that the human spaceflight folks might look at?
When we were designing Webb from the start, because we knew we had to send it to this point that, so again, imagine we're thinking now in the mid-1990s, there was no way of having any sort of servicing capability. Right. So Webb was never designed with servicing in mind. And as a consequence, we made design decisions about how the instruments are arranged that would make servicing highly complex and probably not feasible. If you just look at that, the sun shield configuration, the notion of having something go up there and touch it, it would have to be so gentle that you don't actually buckle your sun shield. Because we have a naked optic, anything that got close to it would have propellant cloud around it and you would get contaminants on the mirror. So it was never designed to be serviceable, and as a consequence, because you don't build that in, you almost forbid it.
All right,
we have another online question. You may have mentioned this, but I didn't catch it. Why is the James Webb Space Telescope launching from South America?
When we were conceiving the mission and we knew that the European Space Agency wanted to be a contributor, they said, well, you know, we want to build some science instruments, and of course that's the fun part, and so they did that. And then we also asked for functional contributions. And we looked at, well, could they build the spacecraft, or could they build this component? And in the end, the thing that we found was the most logical and the cleanest from an engineering standpoint was for them to provide a launch vehicle. And we also needed a certain dollar value of contribution, and so their combination of science instruments and launch vehicle added up to the right amount that we needed them to contribute. Now, in the intervening years, the Ariane 5 has proven to be the world's most reliable rocket. There is no rocket in production today that has had more successful consecutive launches than the Ariane 5. So this is a very precious science asset, both Europe, Canada, and NASA have invested a lot of money in it, and so you want to put it on the safest vehicle, and that's the Ariane 5.
Okay, this is kind of a hypothetical question. But would JWST have been an easier project if you'd had access to a heavy lift launch vehicle like Shuttle in the past or SLS coming up in the future, not only in terms of the mass, but the diameter of objects you could put under a payload shroud?
Unquestionably, had we had SLS as a launch vehicle, you know, in our pockets to pick, the design probably would have been different. You wouldn't have needed to go to a deployable design because you would have had a much larger fairing. You would have had mass to spare, so you wouldn't have cared that you had to carry a big massive tube up to protect you. So you would have put a tube on. It would have looked much more traditional. You design for what you know at the time, and so a lot of the way Webb looks today is a consequence of what the decisions that had to be made in the 90s. And at some point you get too far down the road to say, hey, why don't we redesign for this? Well, you just can't do that.
Joe, I'd like to ask you one.
Sure.
What are some of the pressing science research investigations that you're looking forward to in the near future using DSN?
How much time do I have?
Several minutes.
There are many, of course. There are all the currently operating missions which continue to return lots of science. Juno is on its way to Jupiter, so this is a new mission to Jupiter. The gravitational waves that I described, we are looking at ways that we can use the DSN antennas themselves to test this part or verify this part of Einstein's theory of relativity. In fact, the first effort to test gravitational waves using a slightly different technique than what I described was first done at JPL using the DSN, but it was literally ahead of its time. We didn't have the right kind of stars to do the tests and things like that. We're now into the mode where we can do that. There are some interesting upcoming possibilities with a future mission to Mercury in terms of, again, probing the solar wind. So that's the material that's flowing off the star, as well as doing some additional probing slightly different ways of probing Einstein's theory of relativity. They're, again, thinking about these interplanetary CubeSats, people are already starting to design in or think about how we do CubeSats with missions. And whatever future spacecraft is going, wherever it is, whether it's to Jupiter or to Mars, carrying with it multiple. And so, in fact, in some presentations I've said, or I expanded on this notion of, we've sent one probe into the atmosphere of Jupiter. We sent one probe onto the surface of Titan. Now it's time to do 10. We should be dropping 10. So I think that's clearly one of the things, and it's going to be, in some sense, as I described, a bit of a challenge for the DSN, but that's the kind of challenge we want to have.
Okay, next question.
Yes, I have another question. In the history of astronomy, when a giant leap is known to about happen, like the building of Palomar, for instance, astronomers got together and decided that they needed deeper maps in order to exploit the powers of the new telescope. We know that, of course, Hubble has done many things to prepare for Webb, but I'd appreciate some deeper insight as to how well prepared you feel astronomy is to take full advantage of something like the Webb telescope when it launches.
So in preparation for JWST operation, we'll not only have the deep fields that Hubble has done. They've recently started what are called frontier fields at the Space Telescope Science Institute, where Hubble is again going to be looking very deeply at some different places in the universe. Right now there are two spots, one in the northern hemisphere, one in the southern hemisphere, that Hubble and assets like Chandra and Spitzer have looked very deeply at, radio telescopes as well. So by expanding this to the frontier fields, you'll now have more places in the sky where telescopes have devoted a considerable amount of time, both space assets and ground. And the unique thing about the frontier fields is that they are going to use nature through, the frontier fields are centered on clusters of galaxies. And so you will use that cluster of galaxies to act as a gravitational lens to peer deeper in the universe. So you're getting a boost from your intervening galaxy clusters. So we'll have those. It's actually a very active topic of debate within the science working group for the James Webb Space Telescope to determine what do we need now before we launch. And so they're considering very carefully, do we have sufficient infrared calibrator stars? Do we need to use Spitzer for something like that? So you're right, it's a crucial thing and we're working on it.
Thank you. Joe, did you want to add to that?
No, I think the first thing that popped in my mind was the frontier fields, and then Eric has already described the work that, for instance, Spitzer and other telescopes have done of looking at extrasolar planet atmospheres.
So again, a related question is, how much cross-fertilization is done between the facility class observatories? We're using Hubble and as a prelude to James Webb, but Spitzer, Chandra, right? We're combining observations off of all of them. How are they synergizing each other?
Yeah, astronomers do that pretty natively now, and Joe will certainly confirm this, that people are multi-wavelength. I think if you go back a generation or two in astronomy, people might have been, I'm a radio astronomer, I'm an optical astronomer, and those were the two camps. But now, if you look at someone who's early or mid-career, they have observations across all the wavelengths. So people know if I need to further my field, I'm going to need these kind of X-ray data and this sort of radio data, and that's what I'm going to need from Webb. So that kind of information comes from the community now, and certainly the institutions that run the Hubble or the Chandra, they have committees that are constantly talking to one another about how can we make sure our facilities are maximizing the science.
And some of the images of the day that NASA releases are multi-wavelength images where you've combined them off of several different observatories.
Yes. Yeah.
And actually, if I can add to that, just to emphasize Eric's point, one of the things that's certainly done at some places is you can request time on this telescope and this telescope with the same proposal. So it's actually, as Eric was saying, it's set up so that to think a multi-wavelength or to think about what nature is giving us and how do we exploit our telescopes to the best advantage.
So now you get the combination of complex multi-observatory scheduling.
Yes. Yeah.
All right. Well, I'd like to thank Dr. Eric Smith and Dr. Joe Lazio, our speakers today, for coming and educating us about the future and deep space communications. I'd like to point out to the audience here that when you go out of here into the Milestones Gallery, you can see the Hubble Space Telescope and some of the cameras, some of the instruments that were recently returned off of the Hubble servicing mission, so you can see actual flight hardware and see some of those instruments that these astronomers are using to collect that data and form and test those theories. I'd also like to remind you that there is another event tomorrow at 1 p.m. where we'll be back here at the museum talking about communicating with humans in space, and that'll primarily be looking at the space network and talking to shuttle and space station astronauts. So I invite you back for tomorrow's presentation as well. Thank you all, and that concludes today's talk.